Tonight, the ground beneath Yellowstone seems quiet. Forests stand still. Steam rises slowly into the cold air. But far below this calm landscape, scientists are detecting a vast and restless volcanic system that still holds enormous heat. New discoveries are revealing a structure more complex, more active, and more closely watched than many people realize. Yellowstone is not erupting today, but the questions surrounding what lies beneath it are becoming harder to ignore. Before going deeper, please like the video, subscribe to the channel, and stay with the story as this hidden world begins to unfold. Yellowstone rests high in the interior of North America, where a broad volcanic plateau spreads across northwestern Wyoming and extends toward Montana and Idaho. The land stands at a great elevation, and that height shapes nearly everything seen at the surface. Air moves across open ground with a cool dryness for much of the year. Snow gathers deeply in winter, then lingers across shaded slopes and open meadows long into spring. Summer arrives gently at this height, with bright mornings, cool nights, and afternoon clouds that drift over forests and ridges. The plateau does not appear as a single flat table. It rises and falls in wide undulations, with low hills, open basins, marshy valley floors, and long forested reaches that seem to continue without interruption. Beneath that quiet variety lies a landscape built by volcanism, yet at the surface it first presents itself as a place of water, trees, stone, and weather. The Yellowstone River begins here and crosses the plateau as one of its main organizing lines. It gathers snowmelt and rain, winds through broad valleys, and cuts through layers of volcanic rock. Other rivers and streams join the system, feeding lakes, wetlands, and meadows along their paths. Water slows in some places and spreads into sedges and grasses. In other places it narrows, quickens, and passes over gravel, fallen timber, and dark stone. The pattern of drainage reveals the shape of the land. Basins hold moisture and cold air. Higher ground sheds water more quickly. Spring runoff can be strong, while late summer often leaves smaller channels shallow and clear. At this elevation, the yearly balance of snow, thaw, rain, and evaporation gives the plateau much of its seasonal rhythm. Yellowstone Lake lies near the center of this high country and gives the landscape one of its clearest points of stillness. It is one of the largest high-elevation lakes in North America, and it holds cold water even in summer. Its long shoreline bends around inlets, forested margins, and open arms that reach toward distant hills. Wind can move hard across its surface, turning calm water into short, cold waves. In quiet weather the lake reflects pale sky, scattered cloud, and the dark mass of lodgepole pine standing close to the shore. Around the lake, the ground often appears gentle, but this gentleness can be misleading. Marshes, shallow bays, and drowned timber speak of a place where water levels, sediment, and the slow movement of land have all shaped what is visible. The lake is not separate from the plateau around it. It is one expression of the same broad volcanic basin, filled with water, light, and winter cold. Forests cover much of Yellowstone's surface. Lodgepole pine dominates large areas, forming dense, straight stands that can look almost uniform from a distance. Closer view reveals differences in age, spacing, and recovery after fire. Fire is a natural part of this landscape. Dry summers, lightning, resin-rich wood, and long intervals between wet periods create conditions in which forest burns and then grows again. Charred trunks, fallen snags, saplings, and mature stands often exist close together, showing different moments in a cycle that unfolds over decades. In wetter places, spruce and fir appear, especially in cooler ground and along streams. Aspen grows in patches where light reaches the soil and moisture remains near the surface. Willow thickets gather beside rivers and wet meadows. The plant cover follows temperature, water, and soil, and each of these conditions is shaped by elevation and volcanic ground beneath. The soils of the plateau vary widely. In some places they are thin, stony, and dry, lying over lava and ash-rich deposits that drain quickly. In others they are deeper and darker, holding more moisture and supporting meadows thick with grasses and summer flowers. Many surface materials are young in geological terms. Ancient eruptions spread ash, pumice, and lava across large areas, and later erosion breaks those materials down into sand, silt, clay, and rough fragments. Glaciers also leave their mark. During colder periods of the past, ice moves through parts of this plateau, scraping rock, carrying debris, and shaping valleys and basins. When the ice retreats, it leaves ridges of sediment, scattered boulders, and altered drainage paths. The visible land is therefore not the product of one process alone. Volcanism builds and buries, ice scours and rearranges, water cuts and deposits, wind dries, chills, and clears. The result is a surface that seems calm only because its changes usually move slowly. Mountains frame the plateau on many sides. Their outlines are rarely sharp in every direction, because distance, haze, cloud, and forest soften the horizon. Some ridges rise as dark walls beyond valleys. Others appear as long backs of timbered high ground, with little bare rock showing except on steeper faces. These surrounding uplands help collect snow and direct runoff into the Yellowstone Basin. They also hold the plateau within a broader regional setting, making Yellowstone feel at once open and enclosed. One can see far across meadows and lake water, yet the view often returns to rising ground at the margins. The sense of space comes from width rather than emptiness. Trees, streams, and hills fill the scene, but none of them completely conceal the scale. Wildlife is part of the surface setting and moves through it according to season, elevation, and available forage. Bison cross meadows and roads with slow certainty, following old paths through grassland and thermal clearings. Elk gather in open areas and along forest edges. Wolves pass quietly through timber and valley. Bears range widely between berry patches, carcass sites, meadows, and stream corridors. Waterfowl use the lakes and marshes during the warmer months, while smaller animals remain tied to burrows, brush, and tree cover. The visible life of Yellowstone depends on the surface expression of the plateau cold winters, short growing seasons, rich summer meadows, forest shelter, and abundant water. The land supports life not as a static stage but as an active arrangement of temperature, moisture, and terrain. Even in silence, the plateau conveys motion. Clouds form and dissolve above it. Snowpack deepens and shrinks. Streams swell, then clear. Forest stands recover from fire. Sediment moves grain by grain down slope and into water. The land does not need steep peaks or violent weather to show change. Its changes are persistent, measured, and broad. On this high volcanic plateau, the first impression is not catastrophe, but continuity. Open meadow gives way to forest. Forest opens toward river. River widens toward lake. Mountain margins hold the basin in cool air and winter snow. The entire surface seems settled into a long balance between uplift, erosion, climate, and life. Yellowstone, at this outermost level, appears as a complete landscape in itself, a high country shaped by stone, water, weather, and time, resting in plain view under the slow movement of the sky. Across the Yellowstone Plateau, the most visible signs of underground heat appear where water reaches the surface. These places are not scattered at random. They gather in broad thermal basins, along stream valleys, near lake shores, and across low ground where fractures in the rock allow heat and fluid to rise. From a distance, a hydrothermal area often looks pale and open against the dark forest around it. Trees thin out or disappear. Bare ground shows through in white, grey, yellow, and rust tones. Steam drifts upward in cool air and bends with the wind. Small runoff channels carry mineral-rich water away from springs and spread it across shallow terraces. The whole surface looks altered, not by fire at this moment, but by water that is heated far beyond ordinary ground temperature and brought back into daylight. The word hydrothermal refers to hot water moving through rock. In Yellowstone, this process depends on three conditions that meet in the same place. There is abundant water from snow and rain. There is heat rising from depth. There is fractured rock that allows water to circulate downward and then return upward. Cold water from the surface seeps into the ground through pores and cracks. As it descends, it encounters warmer rock. In some places, it becomes hot enough to remain liquid under pressure. In other places, it turns partly to steam. As pressure changes and pathways open, the heated water rises again. Where it reaches the surface, it creates a wide range of features that differ in appearance, but belong to the same broad system of water, heat, minerals, and rock. Hot springs are the simplest and most widespread expression of that system. They appear as pools, vents, shallow basins, and channels filled with clear or faintly coloured water. Some are quiet and nearly still, with only a slow overflow at the rim. Others bubble steadily as dissolved gases escape or as water circulates upward from below. Their colours can be striking, but those colours follow understandable causes. Pure water often appears deep blue where the pool is clear and wide enough for light to scatter through it. Along the margins, where water cools and becomes shallow, mats of microscopic life may grow in bands of orange, green, brown, or yellow. These organisms are adapted to heat and chemistry that would exclude most other life. They do not grow everywhere in the same pattern, because temperature, acidity, light, and water flow differ from one spring to another. The result is a surface that seems richly painted, though the colours come from mineral deposits, biology, and the movement of light through water. Some hot springs build terraces of white stone around themselves. This stone is not ordinary sediment washed in from elsewhere. It forms from minerals dissolved in the hot water itself. As water rises, cools, and releases gas, the dissolved material can no longer remain fully in solution. It settles out and hardens layer by layer. In limestone-rich thermal systems, this deposit is often called travertine, a form of calcium carbonate. In other areas of Yellowstone, silica. A material related to quartz can build sinter, a hard white deposit that forms low rims, knobby surfaces, and smooth runoff aprons around hot vents. These deposits record movement in slow detail. Water changes course by a few hand widths, and a new rim begins. Flow weakens, and an older channel dries and cracks. A vent becomes more active, and fresh mineral crust brightens around its edge. The hydrothermal surface is therefore never fixed. Even where change is slow, it continues. Geysers are the most specialized features in this landscape. A geyser is a hot spring that erupts intermittently, sending water and steam upward in bursts. This happens only when underground conditions are unusually specific. Heat alone is not enough. Water alone is not enough. A geyser needs a plumbing system of narrow passages, cavities, and constrictions that allow pressure to build. Water deep in that system becomes extremely hot under the weight of water above it, because pressure is high. It does not boil immediately even when its temperature rises beyond the normal boiling point at the surface. When some water higher in the system spills out or flashes into steam, pressure drops suddenly. That drop allows deeper water to boil rapidly. Steam expands with force, pushing water upward in an eruption. After the eruption, the system refills, reheats, and prepares again. Yellowstone contains the world's greatest concentration of geysers because it combines abundant water, strong heat flow, and the right kind of fractured volcanic rock. Even among geysers, behavior varies widely. Some erupt frequently and modestly. Others remain quiet for long intervals and then send high columns of water into the air. Some erupt with regular timing, while others change their rhythm over seasons or years. The reason lies in the complexity of each underground conduit. Small mineral deposits can narrow a passage. Earthquakes can shift water routes. Changes in groundwater supply can alter recharge time. Cooling or heating within part of the system can change how pressure builds. Scientists can describe the general mechanism of geyser eruption with confidence, yet the detailed behavior of any one geyser may still change in ways that remain difficult to predict precisely. The visible eruption is brief, but it depends on a hidden structure that is delicate and constantly adjusted by water, heat, and deposited minerals. Mud pots appear where the hydrothermal process takes on a different surface form. Instead of a clear pool or erupting fountain, there is a thick, bubbling mixture of hot water, fine sediment, and altered clay. These features usually form where steam and hot gases rise through ground that has relatively little liquid water at the surface. Acidic conditions can break down surrounding rock into clay minerals. The result is a soft basin of grey, pink, or tan mud that churns as gas escapes from below. Bubbles swell, stretch, and burst. Small blobs rise and collapse back into the same thick mass. The activity can seem gentle, yet it reflects intense chemical alteration of the ground. Rock is not simply heated. It is changed in composition by hot acidic fluids that dissolve some minerals and leave others behind. Fumaroles are the driest and often the hottest visible thermal features. They are steam vents, openings where gas escapes directly from the ground with little standing water to moderate the release. In cool air, they send white plumes upward that can be seen from great distance. Near the vent, the ground may be stained yellow by sulfur or coated with other mineral crusts left behind as gas cools. The surface around a fumarole can be unstable, warm, and chemically harsh. A fumarole shows how close heat can come to the surface when liquid water is limited in the uppermost ground, where a hot spring reveals a pool and a geyser reveals a pulse. A fumarole reveals the constant outflow of steam and gas. Taken together, these features make Yellowstone's surface seem active even in still weather. Water seeps, overflows, bubbles, flashes to steam, and lays down new mineral crust. The thermal basins are open windows into a shallow part of the system, shaped by circulation rather than by a single event. Their forms depend on rainfall, snowmelt, underground pressure, rock type, chemistry, and the slow building of deposits around vents and channels. At this level, Yellowstone does not yet reveal its deeper structure. It reveals instead a surface where ordinary water meets unusual heat, and where that meeting transforms the ground into pools, terraces, vents, and steaming flats that remain in steady motion under the cool air of the plateau. Much of Yellowstone's volcanic structure is hidden by its own scale. A visitor standing on the ground does not see a single mountain cone, a steep crater wall, or a central peak that clearly marks the heart of the system. Instead, there are forests, lakes, meadows, river valleys, and broad uplands spread across a high plateau. Yet this wide landscape contains one of the largest volcanic depressions on Earth. The central structure is a caldera, a large basin-like collapse formed when a major eruption removes a great volume of magma from beneath the ground and the overlying crust sinks downward. In smaller volcanic settings, a crater can appear as an obvious hollow around a vent. In Yellowstone, the caldera is so wide that it merges into the terrain and becomes difficult to recognize without maps, measurements, and a regional view. The Yellowstone caldera extends for many tens of kilometers across. It does not form a neat circle drawn sharply into the land. Its margins are irregular, softened by later eruptions, faulting, sediment, glacial reshaping, forests, and the ordinary erosion of water and frost. Some edges are marked by scarps, which are steep slopes formed by fault movement, while other parts are hidden under younger lava flows or covered by surface deposits. The result is a structure that exists clearly in geology, but only partly in the eye. One can pass across its interior without ever feeling a rim in the way one would at a smaller crater lake or volcanic cone. The basin is too broad, too altered, and too integrated into the plateau around it. It belongs to the landscape as a whole, rather than standing apart from it. The formation of a caldera begins with eruption, but the defining shape comes from collapse. When a very large volume of magma rises, erupts, or shifts away from the shallow storage region beneath the volcano, the rock above can no longer remain fully supported. Fractures open, blocks of crust begin to subside. The surface drops along ring-shaped faults, which are curved fractures that outline the collapsing area. Instead of one central hole simply blown open from above, the structure forms as the ground settles downward into partly emptied space below. In Yellowstone's case, this process happens during immense eruptions in the deep past, each associated with vast ash flows and the release of volcanic material over very wide areas. The caldera visible today is mainly linked to the most recent of those giant events, which occurs about 630,000 years ago. That age is ancient in human terms, yet recent in geological terms. Since then, Yellowstone does not remain empty or still. The caldera floor is partly filled by younger lava flows, sediments, hydrothermal deposits, lakes, streams, and glacial material. Rhyolite lava, which is silica-rich volcanic rock formed from sticky magma, spreads across parts of the collapsed basin after the major caldera-forming eruption. Because this lava is thick and slow-moving compared with more fluid basalt, it builds broad domes, coulees, and rough surfaces rather than long thin streams. Over time, these younger eruptions soften the caldera's internal relief and cover some earlier structures. The depression remains, but it becomes more complex. What had once been a dramatic collapse feature is gradually reshaped into the broader volcanic plateau visible today. Yellowstone Lake occupies part of this caldera interior and helps reveal the basin's scale. It rests within the larger collapsed region, though not all of the lake lies within the same structural boundaries. Nearby plateaus, thermal basins, and low uplands also sit on or within the caldera floor. The pattern can be difficult to grasp from ground level because the human eye works best with nearby contrasts and clear edges. Yellowstone instead presents a very large form whose parts must be assembled mentally from many separate observations. A broad meadow may lie on the floor of an old collapsed structure. A ridge may mark a faulted margin. A lake basin may reflect later deformation and volcanic filling. None of these features announces the whole by itself. The caldera must be understood as a regional arrangement of landforms, not as one visible cavity. Faults play an important role in making this structure legible. Along parts of the caldera margin, the crust breaks and drops in steps. These fault scarps can appear as linear slopes or breaks in topography, though many are subdued by time and cover. Within and around the caldera, later faulting also reflects the fact that the crust remains mechanically active. The ground has not simply settled once and hardened forever. It continues to respond to heat, stress, fluid movement, and regional tectonic forces. Tectonic refers to the large-scale movement and deformation of Earth's outer shell. Yellowstone sits within a broader region where the crust is being stretched. That regional stretching affects faults, basins, and mountain ranges across the surrounding western United States. The caldera therefore exists within both a volcanic and a tectonic setting, though at the surface these influences are woven together into one landscape. The scale of Yellowstone's past eruptions is often discussed in public language that emphasizes disaster, but the land itself presents a quieter truth. The caldera seen now is not a fresh wound. It is an old volcanic structure that has been modified for hundreds of thousands of years. Forest grows across it, rivers cross it, sediment settles into it, glacial ice once moves across parts of it. Hydrothermal systems continue to mark areas of heat. Yet much of the caldera floor appears as ordinary plateau country. This contrast matters. The significance of the structure lies not in dramatic appearance at the present surface, but in what the structure records about the volume of magma once stored below and the long-lasting heat that remains in the crust. Recognition of the caldera depends strongly on aerial and regional perspectives. From high ground, from topographic maps, from geophysical surveys, and from satellite observations, the broad shape becomes clearer. Boundaries that are difficult to see on foot can be traced through changes in elevation, rock type, fault pattern, and gravity measurements. Gravity surveys help because different underground materials have different densities. A collapsed, partly filled basin may produce a subtle signal distinct from surrounding crust. In the same way, mapping of lava flows and ash deposits helps define what is older, what is younger, and where the major collapse structure must lie beneath the surface arrangement. Scientific understanding of the caldera does not rest on one dramatic site. It rests on many kinds of evidence brought together carefully. Within the Yellowstone landscape, the caldera is therefore both present and concealed. It is present as the broad depression, the pattern of faults, the young volcanic filling, the thermal basins, and the arrangement of uplands and low areas. It is concealed by forests, lakes, sediments, and the sheer breadth of its form. The land does not display its volcanic architecture in a single view. It reveals it slowly, across distance and through measurement. At this surface structural level, Yellowstone is best understood not as one mountain waiting to erupt, but as a vast collapsed volcanic field whose shape lies in plain sight only when the eye steps back far enough to see the whole basin held quietly within the plateau. Yellowstone's broad surface does not reveal its condition through one dramatic sign. It changes slowly, unevenly, and often by amounts too small for the eye to detect. For that reason, scientists watch the region through repeated measurement rather than occasional inspection. The work begins with careful mapping of the land itself, elevation, slope, drainage, rock type, thermal ground, fault traces, and the position of roads, rivers, lakes, and basins are all recorded in detail. A map in this setting is not simply a guide for travel. It is a way of establishing where each visible feature lies so that later changes can be recognized against a stable reference. When the ground rises by a few centimeters over months or years, or when a thermal area expands across a small patch of snow-free earth, those changes become meaningful only because an earlier surface has already been measured and described. On the ground, one of the main tools is the seismometer, an instrument that detects shaking in the earth. Although earthquakes themselves belong to a deeper level of the system, the instruments that listen for them are part of the surface network of observation. Small stations sit in remote places across the Yellowstone region, fixed to stable ground and linked by radio, satellite, or other communication systems. They work continuously through summer heat, winter snow, wind, and isolation. Most of the motion they detect is too weak for people to feel. The instrument records a continuous trace of vibration, from distant earthquakes around the world to nearby fractures within the Yellowstone crust. Scientists compare these signals across many stations to determine where an event occurs, how deep it is, and how strong it may be. A single station hears movement. A network begins to locate it. Another important group of instruments measures the slow motion of the ground itself. Global positioning system stations, fixed securely to bedrock or stable mounts, provide extremely precise positions through time. A station does not merely show where it stands on a map. It reveals whether that point on the land is moving upward, downward, northward, or westward by very small amounts. Over long periods, a pattern emerges. One part of the caldera floor may rise while another remains nearly steady. A basin may subside over several seasons. A region may change direction after an earthquake swarm or a shift in underground fluids. These motions are often subtle, but in a volcanic system, subtle motion matters. It shows that the crust is not rigid in a simple way. It bends, lifts, sinks, and adjusts in response to heat, pressure, water, and the mechanical strength of the rock. Some surface instruments are designed to detect even finer change. Tilt meters measure tiny shifts in ground angle, allowing scientists to see whether the land is leaning slightly in one direction. Strain meters measure deformation within the rock itself, showing whether the crust is being stretched or compressed across very short distances. These signals can be affected by weather, snow load, and temperature as well as by geological causes, so interpretation requires care. A useful Yellowstone record is rarely taken at face value from one instrument alone. It is checked against nearby stations, against seasonal conditions, and against other forms of monitoring. A signal gains meaning when it fits a broader pattern rather than standing alone. Observation also comes from the air and from orbit. Satellite measurements have become one of the clearest ways to track Yellowstone's broad deformation. A key method is radar interferometry, often called INSAR. In simple terms, a radar satellite passes over the same region more than once and sends signals toward the ground. If the surface has moved slightly between one pass and the next, the returning radar pattern changes in a measurable way. With careful processing, scientists can turn those differences into maps of ground motion across very large areas. This method does not depend on clear daylight in the same way that ordinary photography does. It is especially useful for showing how a whole basin changes shape, not just how one point moves. In Yellowstone, such observations help reveal uplift and subsidence patterns that unfold over months and years across the caldera and surrounding plateau. Ordinary images from aircraft and satellites are also important. though they serve a different purpose. High-resolution photography can show the outlines of thermal ground, the growth or decline of vegetation, new sediment fans after floods, shoreline change at lakes, and shifts in the colour and texture of hydrothermal basins. Seasonal snow cover can also help reveal heat. In winter, some thermal zones remain partly free of snow and ice, producing pale, open patches within otherwise frozen surroundings. Repeated imaging allows scientists to map these areas with increasing precision. A change in snow-free ground does not by itself prove a major change in the volcanic system, yet it may indicate altered heat flow or water circulation near the surface. As with all Yellowstone monitoring, the meaning comes through comparison and context. Field observation remains essential even in an age of satellites. Scientists visit thermal basins, stream channels, lake margins, and instrument sites to confirm what remote data suggest. They repair stations damaged by weather or wildlife. They measure temperature in selected streams and thermal runoff channels. They collect water and gas samples from some areas to understand chemistry and change through time. They examine deposits laid down by hot springs and look for signs that runoff paths have shifted. Some work is routine and methodical. Instruments must be maintained, batteries changed, data links checked, and damaged parts replaced. Yellowstone's climate makes this difficult. Deep snow can isolate sites for months. Frozen ground affects some measurements. Spring thaw changes access. Yet without this surface work, the monitoring network would lose reliability. A central feature of this effort is continuity. 1 week of data says little by itself. One unusual month may still fall within the normal range of Yellowstone's behavior. The volcanic field is active, but activity here often means persistent change rather than immediate crisis. Ground rises for a period, then falls. Thermal areas shift modestly. Earthquake swarms come and go. Weather introduces noise into the record. For this reason, scientists build long-time series, records collected steadily over many years. These records make it possible to separate a temporary surface effect from a broader geological trend. They also help establish what ordinary unrest looks like in Yellowstone, a place where motion and heat are expected parts of the system. Public communication is part of monitoring as well. Data from many Yellowstone instruments are available in near real time, and official updates summarize recent earthquakes, deformation, and notable observations. The aim is not to dramatize small changes, but to place them in context. Careful language matters. A measured rise in one area does not automatically indicate magma moving upward. A swarm of small earthquakes does not automatically imply eruption. Observations indicate that Yellowstone remains dynamic, while interpretation must remain grounded in multiple lines of evidence. The landscape is watched patiently from the surface and from space because it changes slowly enough to require discipline, but clearly enough that each careful measurement adds another piece to the picture of a living volcanic region. Beneath Yellowstone, the crust breaks in small and frequent ways. Most of these breaks are too slight to disturb the surface visibly, yet they send waves through the ground that instruments record with great sensitivity. These events are earthquakes, sudden releases of stored stress as rock slips or cracks. In Yellowstone, earthquakes are common. The region is one of the most seismically active parts of the interior western United States, not because it is in constant violent upheaval, but because the crust here is warm, fractured, and mechanically complex. Heat weakens rock. Faults provide surfaces along which movement can occur. Fluids moving through cracks can alter pressure and reduce resistance. Regional stretching of the crust adds another source of stress. The result is a setting in which small earthquakes happen often enough to form an ongoing part of the system's behavior. Most Yellowstone earthquakes are minor. They are detected by instruments rather than felt by people. A great many occur at shallow depths within the upper crust, often several kilometers below the surface. At these depths, rock is still brittle enough to fracture. Brittle means that a material breaks rather than flowing smoothly when stress becomes too great. In deeper and hotter zones, rock can begin to deform more gradually, but in the upper crust of Yellowstone, many rocks still fail in sudden slips and cracks. Each event releases only a small amount of energy, yet together they provide a detailed picture of where the crust is under strain. A map of earthquake locations often shows not one central point, but a broad pattern spread across the caldera, its margins, and nearby fault zones. Some earthquakes occur individually, separated by quiet intervals and scattered across the region. Others appear in swarms. A swarm is a cluster of many earthquakes concentrated in one area over a period of hours, days, or months, without one single large event clearly dominating the sequence. This pattern is common in Yellowstone. Swarms can involve dozens, hundreds, or even more small events, and their timing may seem irregular. Activity may build, slow, shift slightly in location, and then fade. The importance of a swarm lies not in drama but in what it suggests about local conditions. Swarms often indicate that stress is being adjusted across a network of fractures rather than released along one main fault in the manner of a classic main shock followed by aftershocks. In Yellowstone, that adjustment may be influenced by both rock movement and the movement of underground fluids. Fluids matter because water under pressure can change the mechanical behavior of rock. When hot water or gas occupies cracks, it can help open pathways or reduce the friction that keeps a fracture locked. A pressure change in one part of the system may therefore encourage small slips nearby. This does not mean that every Yellowstone swarm has one simple cause. Some reflect tectonic stress. Some are linked partly to fluid motion, and many likely involve both. Scientists examine the depth, shape, timing, and wave characteristics of the events to understand what kind of process is most consistent with the data. Observations often indicate a complex interaction rather than a single clean mechanism. The crust beneath Yellowstone is not a dry block of stone. It is a cracked, heated, fluid-influenced environment in which several forms of stress and pressure meet. Faults provide the main planes of weakness along which many earthquakes occur. Some faults are long regional structures that extend beyond the national park. Others are shorter or more subtle breaks within and around the caldera. A fault is a fracture in the earth along which rocks on either side have moved relative to one another. That movement may be vertical, horizontal, or a mixture of both. Around Yellowstone, many faults are normal faults, meaning one side moves downward relative to the other as the crust stretches. This style of faulting fits the broader tectonic setting of the region, where the crust is being pulled apart over geological time. Even very small slips on such faults can produce measurable earthquakes. The surface may show only a subdued scarp or no obvious feature at all, yet the underground fracture remains a place where stress can accumulate and release. Depth patterns are especially informative. Many Yellowstone earthquakes occur in the upper several kilometers of crust, where hydrothermal fluids are active and where brittle failure is common. Some occur deeper, suggesting that stress extends downward into hotter levels. Depth alone does not identify the cause of an earthquake, but it helps narrow the possibilities. A shallow cluster beneath a thermal basin may reflect local fracture adjustment associated with fluid circulation. A broader cluster along a mapped fault zone may fit regional tectonic movement more closely. Scientists therefore treat earthquake catalogues not as isolated events, but as a layered record of where the crust responds most readily. Each small signal adds to a long-term map of weakness, pressure, and motion. From time to time, Yellowstone experiences larger earthquakes that are felt widely. The most significant historical example in the greater region is the Hebgen Lake earthquake of 1959, which occurs just west of the present caldera area. It is a major tectonic event rather than a caldera-forming volcanic episode, yet it strongly affects the Yellowstone region. It causes severe ground shaking, fault scarps, landslides, and loss of life. It also reminds scientists that Yellowstone must be understood as both a volcanic and a tectonic setting. Large earthquakes in the surrounding region can alter local stress fields, affect hydrothermal behavior, and change groundwater flow. Even so, most Yellowstone seismicity remains far smaller. The day-to-day pattern is dominated by minor events, the kind that reveal persistent underground adjustment rather than immediate large-scale rupture. Seismic waves from these earthquakes allow scientists to do more than count events. The waves themselves carry information about the rock they pass through. Fast waves slow down in hotter, more fractured, or partially molten material. Some wave types weaken strongly in fluid-rich zones. By comparing how waves travel between many earthquakes and many stations, researchers infer variations in temperature, crack density, and rock properties beneath Yellowstone. In that sense, earthquakes act as both symptoms and probes. They show where rock is breaking, and the waves they generate help illuminate the material through which they move. This makes the earthquake record especially valuable in a region where much of the important structure lies hidden below the surface. Even with all this information, caution remains essential. An increase in earthquakes does not automatically mean an eruption is approaching. Yellowstone commonly produces swarms without any eruption following. Earthquakes are a normal expression of an active crustal system. At the same time, they are never ignored, because changes in earthquake rate, depth, or location may indicate that underground conditions have shifted. Scientific concern therefore rests on patterns, not on isolated events. What matters is whether the seismicity fits the long record of expected unrest or departs from it in a sustained and meaningful way. Beneath the park, the crust continues to crack, slip, and adjust. These motions are usually small, often clustered, and always informative, forming a constant hidden rhythm under the forests, lakes, meadows, and thermal basins of the Yellowstone Plateau. The Yellowstone surface does not remain at one fixed elevation. Over months, years, and decades, parts of the ground rise while other parts sink. These changes are usually small in daily life, far too small to notice while walking across a meadow or standing beside a hot spring. Yet when measured carefully, they show that the crust above Yellowstone behaves less like a rigid shell and more like a thick lid that can bend, swell, relax, and settle. This slow changing of shape is called deformation. In a volcanic region, deformation is one of the clearest signs that pressure, heat, fluids, or stress are changing below the surface. At Yellowstone, deformation is persistent enough to be one of the defining features of the modern system, though it rarely proceeds in a simple or uniform way. The floor of the caldera has experienced repeated episodes of uplift and subsidence. Uplift means the ground moves upward, subsidence means it moves downward. These terms sound straightforward, but in Yellowstone they describe patterns that can vary from one basin to another and from one period to the next. A central area may rise for several years and then slow. A nearby area may begin to sink. The amount of motion may measure only a few centimeters in a year. Yet across a wide region, even that modest change is significant. It suggests that forces beneath the ground are acting over large areas, not merely at one narrow crack or one isolated spring. The crust is responding as a broad structure. One important reason for this motion is pressure from fluids and heat beneath the surface. Hot water, steam, and gases move through cracks and porous zones in the shallow crust. When pressure builds in one part of that system, it can push the overlying rock upward slightly. When pressure is released, the same area may settle. The hydrothermal system therefore plays a major role in near-surface deformation. This does not mean that every pulse of uplift is caused only by hot water. Deeper changes in the crust may also contribute. Still, Yellowstone observations often show that shallow fluid movement is an essential part of the story. The land rises and falls not only because of molten rock at depth, but also because water and steam are active within the upper kilometers of crust. The crust itself also matters. It is not equally strong in every direction or at every depth. Some layers are dense and resistant. Others are heavily fractured, altered by heat, or weakened by older volcanic structures. When pressure changes below, the overlying rock does not respond like a perfectly elastic plate. Elastic means a material changes shape under force, and then partly returns when the force is removed. Yellowstone rock shows some elastic behavior, but it is also shaped by fractures, faults, temperature, and time-dependent bending. One area may lift broadly and gently. Another may respond more abruptly along pre-existing faults. A shallow basin filled with sediments may behave differently from a ridge of stronger volcanic rock. The pattern of deformation therefore reflects both the source of pressure below and the mechanical character of the crust above. Yellowstone Lake and the surrounding caldera floor offer some of the clearest examples of this slow motion. Measurements over time have shown that the central caldera does not remain level. Broad uplift has occurred in some periods, followed by slowing or reversal in others. The changes are not random noise. They form maps of bulging and sagging ground that can be tracked across years. These maps are especially useful because they show scale. A single station can reveal motion at one point, but a wider deformation field shows whether the land is arching upward like a broad dome, tilting, or sinking into a gentle basin. In Yellowstone, such patterns often extend over many kilometers, confirming that the underlying causes are regional within the caldera rather than merely local disturbances at one spring or vent. Earthquakes can interact with these changes in elevation. A swarm of small earthquakes may accompany a shift in uplift rate, or occur during a period when pressure is redistributing through faults and fractures. In some cases, deformation appears to continue quietly with little notable earthquake activity. In others, earthquake sequences and ground motion together suggest a linked episode of underground adjustment. The relationship is not always simple. A rise in the land does not require a dramatic burst of earthquakes, and a swarm does not always produce a large visible deformation signal. Yellowstone's importance lies in the combination of evidence, seismicity, ground motion, thermal behavior, and fluid chemistry must be considered together before scientists can judge what kind of process is most likely at work. The timescale of deformation is also important. Changes can continue over several years and then fade. This long pace sets Yellowstone apart from the kind of volcanic inflation that may precede some smaller eruptions over short intervals. Inflation means swelling caused by increased pressure below. Yellowstone does experience inflation and deflation, which is the opposite process of pressure release and settling. but these changes often unfold over broader areas and longer periods. That slower rhythm reflects the scale and complexity of the system. Pressure may be redistributed through large rock volumes, long fracture networks, and extensive hydrothermal zones. The system does not respond like a narrow pipe leading directly upward. It responds like a broad, layered, partly flexible crust over a varied set of underground reservoirs and pathways. Weather and surface conditions can complicate the record. Heavy snow loads press on the crust seasonally. Water from melting snow enters the ground and changes pore pressure, which is the pressure of fluid within spaces in rock and sediment. Temperature affects some instruments and influences the shallow subsurface. These effects must be separated from deeper geological causes. Scientists do this by comparing many years of observations and by looking for patterns that extend beyond seasonal cycles. A brief winter subsidence caused partly by snow load is not interpreted the same way as a multi-year uplift centered within the caldera. Yellowstone monitoring depends on this careful distinction between short-lived surface forcing and sustained crustal deformation. Deformation also reminds scientists that Yellowstone remains active even without eruption. A quiet surface does not mean a static interior. The land itself records ongoing adjustment, pressure builds, migrates, and relaxes. Fluids collect and disperse. Faults accommodate small motions. Heated rock expands slightly and later contracts. The caldera floor responds as a living structure in geological terms, moving enough to be measured but slowly enough that the surrounding forest, rivers, and roads continue their ordinary appearance. This contrast between visible calm and measured motion is one of the clearest features of Yellowstone science. At this level of observation, the crust appears as a broad moving cover above deeper sources of heat and pressure. It rises in places, sinks in others, and changes its pattern over time. The motion is real, measurable, and scientifically important, yet it does not point automatically toward eruption. It shows instead that the Yellowstone system remains dynamic within the upper crust. The ground behaves like a slow surface expression of hidden pressure, responding not in sudden continuous violence, but in gradual pulses of uplift and subsidence that mark the steady breathing of the caldera floor. Across Yellowstone and far beyond its present park boundary, the volcanic past remains visible in the rocks spread over the land. These rocks do not stand in one neat sequence exposed from top to bottom. They appear in cliffs, road cuts, canyon walls, ridges, meadows, and distant plateaus, each place showing only part of the record. Taken together, they reveal that Yellowstone has produced repeated eruptions over millions of years, and that the present plateau is only the latest expression of a much longer volcanic track. At the surface, this history is preserved in lava flows, welded ash deposits, loose volcanic sediment, and altered rock that has been changed by heat and water. The land carries the evidence quietly. A grey cliff may be the hardened remnant of a pyroclastic flow, a fast-moving current of hot ash, gas, and rock fragments. A rounded hill may be a rhyolite lava flow weathered by frost and stream erosion. A pale layer in a distant basin may be ash that settles from the sky after a major eruption. The surface geology records not one single event, but a series of volcanic episodes separated by long intervals of cooling, erosion, and landscape change. The deeper history of the Yellowstone volcanic system stretches southwest across the Snake River Plain, a long volcanic track that marks the movement of the North American tectonic plate over a long-lived mantle heat source. As the plate moves, major volcanic centers appear in sequence. Older calderas and volcanic fields now lie to the southwest, while Yellowstone marks the present northeastern end of that chain. This history is not visible as one continuous crack or ridge on the surface. It is visible through the age and distribution of volcanic rocks. Older eruptive centers have cooled, eroded, and partly subsided into the plain, while younger activity is concentrated beneath the Yellowstone Plateau. At the present surface, the Yellowstone region shows the latest and most elevated volcanic expression of this long path, yet it also contains rock that helps connect it to that older regional history. Within the Yellowstone Plateau itself, one of the most important surface records comes from rhyolite. Rhyolite is a silica-rich volcanic rock formed from sticky magma because the magma is viscous, meaning it resists flowing easily. Rhyolite eruptions often behave differently from the more fluid basalt seen in many other volcanic provinces. When rhyolite reaches the surface as lava, it tends to pile up in thick flows and domes rather than spread rapidly in thin sheets. These flows cool into rock that can be dense, glassy, banded, or rich in crystals depending on how the lava moves and solidifies. On the Yellowstone Plateau, many younger surface rocks are rhyolitic lava flows erupted after the last great caldera-forming event. These flows fill parts of the caldera, build broad plateaus and ridges, and cover older structures beneath. In outcrop, they often show flow banding, subtle layering produced as the lava stretches and folds while still moving. They may also contain obsidian-like glassy zones, pumice-rich margins, and fractured surfaces broken into angular blocks by cooling and later weathering. Some rhyolite flows form striking cliffs and canyon walls. In Yellowstone's Grand Canyon, for example, erosion cuts through volcanic rocks and hydrothermally altered zones, exposing the varied materials that make up the plateau. The canyon itself is carved later by the river, yet the walls show how volcanic deposits differ in strength and texture. Harder units may form ledges. Softer or more altered units weather back into slopes. Colours vary from grey and pink to yellow and red, often influenced by oxidation and hydrothermal alteration rather than by original lava colour alone. These surface exposures help geologists reconstruct what erupts, what flows, and what later changes under heat and circulating fluids. The volcanic past is not preserved as a simple stack of untouched deposits. It is preserved in rocks that have been cut, altered, buried, and revealed again. One of the most distinctive materials in Yellowstone's surface record is welded tuff. Tuff is rock formed from volcanic ash and fragments that settle and harden. Welded tuff forms when hot ash and pumice fall or flow. Deposits remain so hot after emplacement that the particles fuse together under their own weight. In large explosive eruptions, pyroclastic flows spread across great distances as dense, ground-hugging currents. When these currents stop and cool, they can leave thick sheets of ignimbrite, the rock product of such deposits. Some of Yellowstone's most important ancient eruptive units belong to this category. They preserve the surface remains of eruptions far larger than any ordinary lava flow in welded tuff. Flattened pumice fragments may appear stretched into lens-like shapes, showing that the deposit compacts while still hot. Crystals broken from magma are mixed through a fine ash matrix. Cooling joints may divide the rock into columns or blocks. These features allow geologists to identify ancient ashflow sheets even where erosion has removed much of their original extent. The Lava Creek Tuff is one of the best-known examples associated with Yellowstone's most recent caldera-forming eruption. Parts of this unit remain exposed in and around the region, while much of it has been eroded or buried. Its presence at the surface helps define the scale of that eruption and the position of related structures. Other older major eruptive units, linked to earlier caldera systems in the Yellowstone hotspot track, are found farther southwest. Surface geology therefore connects Yellowstone not only to its own recent past, but to earlier volcanic centers along the same broader system. Each welded ash deposit marks an eruption that empties a large shallow magma body enough to trigger collapse. Yet at the surface today, these great events are known mainly through stone layers and erosional remnants, rather than through dramatic intact landforms. Loose volcanic materials also survive in the landscape. Pumice, ash-rich sediment, and reworked volcanic gravel can accumulate in basins and stream valleys. Much of this material is not preserved exactly where it first lands. Water and wind transport it. Glaciers later disturb it in some areas. Rivers cut through it and redeposit it downstream. Even so, volcanic grains remain recognizable under close study. Their chemistry links them to specific eruptive sources. Their distribution helps map the original reach of an eruption. At the outcrop scale, they may appear modest, just a pale bed within ordinary sediment. Scientifically, they serve as time markers and fingerprints of volcanic events. Surface alteration adds another layer to the record. Hot water changes volcanic rock chemically, turning glassy material into clay minerals, depositing silica in cracks, and staining surfaces with iron compounds and sulfur. Hydrothermal alteration can weaken rock so that erosion acts on it more quickly. It can also preserve pathways of ancient hot fluid circulation, giving clues to where heat has long been concentrated. A rock seen at the surface today may therefore tell two stories at once: the story of eruption and the later story of heating, fluid movement, and chemical change. Read across the Yellowstone region, the surface rocks show a long volcanic history written in lava, ash, welded deposits, and altered stone. The plateau is not merely a scenic highland, it is the exposed upper record of repeated eruptions, collapse, filling, weathering, and erosion. The rocks do not speak in one voice, but together they show that Yellowstone's present landscape stands on the surface remains of a major volcanic past, preserved in quiet exposures across the land. The ash from Yellowstone's largest eruptions does not remain close to the source. Fine volcanic material rises high into the atmosphere and then travels far beyond the plateau, carried by prevailing winds across plains, river basins, and distant uplands. At the surface today, this ash often survives not as a dramatic blanket visible to the eye across modern landscapes, but as thin layers preserved in sediments, soil profiles, ancient lake beds, and exposed rock sequences. These layers are among the most far-reaching records of Yellowstone's volcanic history. They show that the effects of major explosive eruptions extend well beyond the caldera itself, spreading fine particles across much of a continent. The surface evidence of this spread is often modest in appearance. A pale band only a few centimeters thick in a sediment outcrop may represent ash that once falls from a sky darkened over a vast region. A layer within an ancient lake deposit may hold grains that drift downward through water after days of settling from the air. The significance lies not in thickness alone, but in distribution. Volcanic ash consists of fine fragments produced when gas-rich magma is broken apart violently during eruption. These fragments are not the soft grey residue of burned wood that the word ash suggests in ordinary language. They are sharp particles of volcanic glass, crystals, and tiny rock fragments. When magma rich in dissolved gas expands rapidly, it shatters into countless pieces. The smallest fragments are light enough to remain suspended for long periods in rising eruption columns and spreading ash clouds. In powerful eruptions, the eruption column can reach great heights, entering levels of the atmosphere where winds move steadily over long distances. From there, ash begins to settle out according to grain size, wind speed, turbulence, moisture, and the duration of the eruption. Coarser fragments fall closer to the source. Finer particles may travel hundreds or even thousands of kilometers before coming to rest. The ash record linked to Yellowstone's major eruptions is therefore broad and layered. Material from the most recent Great Caldera-forming eruption, associated with the Lava Creek Tuff, has been identified across wide areas of North America. The same is true for ash linked to older Yellowstone hotspot eruptions farther southwest along the volcanic track. At the surface, these ashes are often found not in the open modern soil, where erosion and biological mixing may disturb them, but in protected settings where sediments accumulate steadily and preserve a chronological sequence. Lakes are especially useful. A quiet lake floor receives fine material year after year. If volcanic ash falls into such a lake, it may form a distinct layer between ordinary sediments. Marshes, basins, and low-energy river deposits can preserve ash in similar ways. Once buried, the layer may remain intact for very long periods unless later erosion cuts into it. Identification of Yellowstone ash relies on more than color or texture. Many ash beds from different volcanoes can look similar in the field. Scientists therefore examine the mineral content and chemical composition of the glass shards. Even tiny particles retain a chemical signature that reflects the composition of the magma from which they came. By comparing these signatures with known eruptive units, geologists can match a thin, distant ash bed to a specific volcanic event. This approach has turned scattered sediment exposures into a continental-scale record of eruption fallout. What appears at first to be an isolated pale seam in one state may correspond exactly to layers found in other states, all linked to the same eruption cloud moving across the atmosphere. Surface geology thus extends Yellowstone's reach far beyond the park through the patient matching of these fine deposits. The distribution of ash also shows how eruption clouds interact with the atmosphere. Winds at high altitude do not blow equally in all directions at all times. They form prevailing paths that can carry ash more strongly eastward or southeastward, depending on season and atmospheric conditions. As a result, ash blankets from major eruptions are often uneven in thickness and extent. One region may receive a substantial layer, while another at a similar distance receives much less. This pattern matters because it helps reconstruct not only the size of the eruption, but also the environmental setting in which the ash spread. The atmosphere becomes part of the geological record. Surface ash layers preserve not just volcanic fragmentation, but a moment in ancient air circulation. Thickness decreases with distance, though not always smoothly. Near the source, ash and pumice may accumulate in much greater depth, especially where pyroclastic flows and heavy fallout overlap. Farther away, the layer may thin to centimeters or even millimeters. Yet even a very thin layer can be scientifically important if it is chemically distinctive and widely traceable. In continental sediments, such a layer becomes a time marker, a horizon that connects different landscapes to the same moment in geological history. A river terrace deposit, a prairie basin, and a mountain lake core may all preserve the same ash fall from Yellowstone. In this way, a single eruption becomes a reference plane spread through many archives of the land. Ash affects the surface environment in many ways at the time of deposition. Fresh ash can blanket plants, enter streams, alter water chemistry, bury soil, and reduce sunlight reaching the ground. Fine particles can be carried again by wind after deposition, especially in dry open regions. Over longer periods, Ash weathers into clay minerals and contributes to soil development. In some places it is mixed into ordinary sediment so thoroughly that only laboratory work reveals its volcanic origin. The surface record therefore changes with time. A fresh ash blanket becomes a pale layer, then a weathered horizon, then a chemical signal within older sediment. Its form changes, but its origin can still be recovered. In Yellowstone's case, the widespread of ash is one of the clearest signs that the volcanic system has influenced landscapes on a continental scale during its largest eruptions. The caldera and plateau contain the local structural record, but the ash beds carry the same history outward into distant regions. They are quiet evidence of atmospheric transport following explosive fragmentation of magma. At the surface, they survive in exposures that seem almost understated. A thin band, a pale seam, a slight change in grain texture, a concentration of glass shards under a microscope. Yet these subtle traces map the path of ancient eruption clouds across North America, and show that the Yellowstone system must be read not only in the rocks near its centre, but also in the fine airborne deposits left far away, settled slowly across the land and preserved in layers of sediment where time keeps a careful record. Below the visible landscape of Yellowstone, and below the shallow thermal basins where hot water reaches the surface, the upper crust contains a broad zone of stored heat and partially molten rock. This region is often described in simple language as a magma chamber. Yet that phrase can mislead if it suggests a single underground cavern filled with freely sloshing liquid. Observations do not support such an image. The upper crust beneath Yellowstone is better understood as a complex reservoir zone, made of rock that is partly molten in places, mostly solid in others, and threaded by hotter and cooler regions, crystal-rich mush, fractures, and pockets where melt becomes more concentrated. A mush is a mixture of crystals and molten material that behaves neither like a fully solid block nor like an open pool of liquid. In Yellowstone, this mixed character is essential. It explains why the system can remain hot and dynamic for long intervals without needing to contain one vast empty chamber of liquid magma. This upper crustal reservoir lies several kilometers below the surface, within rock that has been heated and reworked repeatedly over time. It exists because magma rising from deeper levels does not simply pass directly upward in one uninterrupted path. Some of it stalls, cools partly, crystallizes, releases gases, and changes the temperature and composition of the surrounding crust. Fresh injections from below can then reheat older material, add new melt, and remobilize parts of what had become more rigid. Over long periods, this process creates a large storage region with uneven proportions of liquid, crystals, and solid framework. In some volumes, melt may form a relatively small fraction of the rock. In others, the proportion may be higher. The reservoir, therefore, has internal structure. It is not one material throughout, but a varied body whose physical state changes from place to place. Geophysical studies help reveal this hidden arrangement. Seismic waves slow down when they pass through hotter and more partially molten material, because such material is less rigid than colder solid rock. Beneath Yellowstone, certain zones in the upper crust show this reduction in wave speed, indicating that the rock there is unusually hot and contains some melt. The data do not imply a single perfectly bounded chamber with sharp walls. Instead, they point to a broad anomalous region, meaning a region whose properties differ from the surrounding crust. In this case, the anomaly reflects elevated temperature and partial melt. The boundaries are gradual rather than absolute. Rock becomes hotter, more melt-rich, or more fractured across a transition zone rather than changing instantly from fully solid to fully liquid. This reservoir occupies only part of the crustal volume beneath Yellowstone, and even within that part, the molten fraction is not everywhere high. That detail matters. For rock to erupt easily, melt usually needs to be sufficiently connected that it can move through the crystal framework and gather into pathways or pockets. If melt remains dispersed between abundant crystals, the material may stay too stiff to flow as a large eruptible body. Yellowstone's upper crustal storage zone appears to contain substantial partial melt, but much of it is thought to exist in a crystal-rich state, rather than as a uniformly mobile liquid mass. This is one reason scientists describe the system with care. Heat is present. Melt is present. Yet the physical condition of that melt determines whether the reservoir behaves as stored hot mush or as a body capable of feeding eruption more directly. The rock framework surrounding and containing this reservoir is also important. The upper crust beneath Yellowstone has been built and modified by repeated volcanism, collapse, faulting, and hydrothermal alteration. Older intrusions, ancient eruptive deposits, and structurally weakened zones all influence where magma accumulates and where it stalls. The reservoir is therefore not only a product of temperature, it is also shaped by the architecture of the crust. Some regions may act as barriers where dense or cooler rock slows ascent. Other regions may serve as storage horizons where magma spreads laterally. Ring faults left by earlier caldera collapse, fractures formed during regional stretching, and the contrast between different rock units all help define where partial melt can persist. The reservoir belongs to the history of Yellowstone's crust as much as to its present heat. Within the upper storage zone, melt does not remain chemically unchanged. As magma cools, crystals grow from it. Those crystals remove certain elements from the remaining liquid, changing the composition of what remains molten. At the same time, fresh magma entering from below may have a different temperature and composition. Mixing can occur, though not always completely. Parts of the reservoir may therefore contain melt that has evolved chemically through cooling and crystal growth, while other parts may show influence from deeper, less evolved input. These internal differences affect density, viscosity, gas content, and eruptive potential. Viscosity is a measure of resistance to flow. Silica-rich Yellowstone melts are generally viscous compared with hotter basaltic melts, and that high viscosity influences how the magma moves and what kind of eruptions it can produce if it reaches the surface. Storage in the upper crust also affects the caldera above. Heat from the reservoir helps sustain the hydrothermal system. Pressure changes within melt-rich or fluid-rich parts of the zone may contribute to uplift and subsidence of the ground. Earthquakes may occur along the margins where stress is redistributed through faults and fractures. The reservoir is therefore not an isolated body hidden below an otherwise separate landscape. It interacts with the overlying crust in many ways, though those interactions are often indirect. The surface does not mirror the shape of the reservoir exactly. A thermal basin above does not mark the edge of a melt pocket with precision. Still, the long persistence of widespread heat at the surface depends on this upper crustal storage region, remaining warm enough to drive circulation and mechanical change. One of the most important scientific advances in recent decades has been the move away from simple chamber models toward this more distributed picture. Earlier public imagination often pictured volcanoes as being fed by large underground caverns, full of liquid magma waiting beneath a lid of rock. In some volcanic settings, such imagery can capture part of the truth in a rough way. At Yellowstone, the evidence indicates a more complicated and less dramatic structure. Partial melt is distributed through a broad crustal volume. Some regions are more melt-rich than others. Some are likely too crystal-rich to move easily. The reservoir behaves as a heterogeneous system, meaning a system made of different physical states and materials rather than one uniform mass. This upper crustal reservoir zone is the first major hidden layer beneath the visible Yellowstone surface, where molten material becomes an essential part of the story. Here, heat is stored not in a single underground lake of magma, but in a large, varied body of hot rock, crystals, and interconnected melt. It is a region of persistence rather than simplicity, shaped by repeated input, partial cooling, and the mechanical structure of the crust. At this depth, Yellowstone begins to reveal its interior as a long-lived volcanic system, in which the boundary between solid and liquid is neither sharp nor fixed, but spread through a reservoir that remains partly molten beneath the plateau. Within Yellowstone's upper crustal reservoir, magma is not a single simple substance. It is a changing mixture of liquid rock, solid crystals, and dissolved gases, all held within a framework that shifts with temperature, pressure, and time. To understand what this means for Yellowstone, it helps to begin with the material itself. Magma is molten or partly molten rock, stored beneath the surface. When it contains a large amount of silica, as much Yellowstone magma does, it tends to be thick and resistant to flow. That thickness affects how crystals grow, how gas is trapped or released, and how easily the material can move through the crust. The behavior of magma depends not only on its heat, but also on how much of it is actually liquid, how many crystals have formed within it, and how much gas remains dissolved in the melt. The molten part of magma is the liquid phase, the part capable of flowing if it is sufficiently connected. This liquid contains a mixture of chemical elements, mainly oxygen, silicon, aluminum, sodium, potassium, calcium, iron, and magnesium, combined into a high-temperature silicate melt in Yellowstone. The melt is typically rich in silica, which means many of the atomic bonds within the liquid create a more connected internal structure than in low-silica basaltic melt. That internal structure makes the liquid more viscous. A highly viscous melt flows slowly and resists deformation. It does not move through cracks and conduits as easily as a thinner melt would. At the same time, it can trap gases more effectively, especially when pressure begins to drop. This combination of high viscosity and dissolved gas is one reason silica-rich volcanic systems can produce explosive eruptions under the right conditions. The solid part of magma consists mainly of crystals. These crystals grow as the melt cools or changes in composition. Crystallization does not happen all at once. Different minerals begin to form at different temperatures and under different conditions. In Yellowstone-type rhyolitic systems, common crystals may include quartz, feldspar, and smaller amounts of other minerals. As crystals grow, they remove certain elements from the remaining liquid. This process changes the composition of the melt left behind. The remaining liquid may become even richer in silica and certain volatile elements. Volatile means an element or compound that can enter a gas phase relatively easily, especially as pressure falls. Water is the most important volcanic volatile, though carbon dioxide, sulfur compounds, chlorine, and fluorine may also be present. As the crystal fraction increases, the magma becomes less like a liquid and more like a crystal-supported mush. The balance between melt and crystals is one of the most important physical properties in the Yellowstone system. When melt makes up a large connected fraction of the material, the magma can move more readily. When crystals dominate, movement becomes more difficult. The material may still be hot and partly molten, yet mechanically stiff. In such a state, the reservoir stores heat and retains melt without necessarily being ready to erupt. This distinction matters greatly. A hot subsurface body with partial melt is not automatically an eruptible magma body. The crystals can form a framework that locks much of the material in place. For magma to move upward effectively, enough melt must be present and connected, and the surrounding crust must provide a path. The amount of liquid rock is therefore more significant than temperature alone when scientists consider eruption potential. Gas provides the third essential part of the picture. In deep magma, gases are often dissolved invisibly within the liquid because pressure is high, as long as the pressure remains strong. Much of that volatile material stays in solution, much as gas can remain dissolved in a sealed bottle of mineral water. As magma rises or pressure otherwise decreases, the dissolved gas begins to separate into bubbles. This process is called exsolution. In a low viscosity melt, bubbles may rise and escape relatively easily. In a viscous rhyolitic melt, bubbles can remain trapped, grow, and increase internal pressure. The expansion of gas can fragment magma into ash and pumice if the pressure release becomes rapid enough. This is one of the fundamental mechanisms behind explosive volcanism. The magma is not driven upward only by buoyancy or heat. It is also pushed and disrupted by expanding gas. In Yellowstone's upper crustal reservoir, gas does not simply wait passively inside the melt. It affects density, pressure, and the ability of the magma to separate into different regions. Gas-rich melt may rise relative to denser crystal-rich material. Gas may collect in pockets if the physical conditions allow it. Some gas may also escape gradually through fractures or through hydrothermal circulation above the magma-bearing zone. The presence of a large hydrothermal system at Yellowstone shows that heat and fluid transfer are ongoing. Though the exact relationship between gas released from magma and gas moving through the shallow crust can be complex, observations indicate long-term degassing in the broader system, but it remains uncertain how much gas is stored in any one part of the reservoir at a given time and how efficiently it can escape. Melt, crystals, and gas therefore create a material that is always evolving. A batch of magma emplaced into the crust begins to cool. Crystals form. The remaining melt changes composition. Gas may remain dissolved, separate into bubbles, or escape. Fresh-hotter magma arriving from below may reverse part of that cooling trend by adding heat and new material. It may melt some crystals back into liquid, reduce viscosity in part of the reservoir, or stir previously separated zones together. The result is not a static underground body but a dynamic one, capable of shifting from more rigid to more mobile states in different areas and at different times. Yellowstone's reservoir is best understood as a living thermal and chemical system, though it changes on timescales much longer than ordinary human experience. One consequence of this evolving mixture is that the reservoir may contain zones with different eruptive significance. A broad volume may have enough heat to register clearly in geophysical studies, yet only a smaller portion may contain melt-rich material that could gather and move. That is why scientists distinguish between total partially molten volume and eruptible magma volume. The first may be large, the second may be much smaller. This distinction reduces confusion in public discussion. A large reservoir does not mean that all of it is available for immediate eruption. Much of it may be crystal-rich, mechanically stiff, and incapable of rapid ascent without further heating, melt segregation, or pressure change. At Yellowstone, the material character of magma helps explain both the persistence of volcanic heat and the rarity of actual eruptions in the recent geological past. The system stores enormous thermal energy, yet much of that energy resides in hot crystal-rich rock and distributed partial melt rather than in one vast mobile liquid body. The melt that is present is viscous, compositionally evolved, and sensitive to gas behavior. Crystals stiffen it. Gas can energize it. Pressure and temperature continually shift the balance. In this upper crustal region, magma is not merely molten rock. It is a changing mixture whose internal proportions determine whether Yellowstone remains in a state of stored volcanic heat or moves closer to conditions in which some part of that stored material can begin to rise. Above the upper crustal magma reservoir, and partly within the shallowest levels of heated rock, Yellowstone contains a vast underground system of circulating fluids. These fluids are mainly water, though they also include steam, dissolved minerals, and gases released from hot rock and magma at depth. At the surface, they appear as geysers, hot springs, mud pots, and fumaroles. Below the surface, they move through fractures, pores, brecciated rock, and altered mineral zones in ways that are far more complicated than the visible features suggest. The shallow subsurface is therefore not an empty layer between the surface and the magma-bearing crust. It is an active hydrothermal zone filled with water under changing temperature and pressure, and shaped continuously by the rock through which that water passes. Most of the water in Yellowstone's hydrothermal system begins as ordinary precipitation. Snow falls across the plateau in winter, rain reaches the ground in warmer months, and meltwater enters streams, soils, and fractures. Some of this water remains near the surface and returns quickly to rivers and lakes. Some seeps downward into permeable rock. Permeable means that a material contains connected openings through which fluid can move. In Yellowstone, permeability is not distributed evenly. Some rocks are dense and poorly connected, others are heavily fractured by faulting, cooling cracks, collapsed structures, or the chemical weakening caused by earlier fluid circulation. These connected pathways allow water to descend until it encounters much hotter conditions. There the water begins to warm, expand, dissolve minerals, and in some cases separate partly into steam. Pressure controls much of what happens next. Deep below the surface, water can remain liquid at temperatures far above the normal boiling point because the weight of overlying rock and water keeps it compressed. As that hot water rises, pressure falls. Under the right conditions, some of the liquid flashes into steam, meaning that it changes rapidly into vapor as boiling becomes possible. This phase change strongly affects the surrounding system. Steam occupies far more volume than the same mass of liquid water, so its formation changes pressure, movement, and the chemical distribution of dissolved substances. In narrow conduits, this can help trigger geyser eruptions. In broader zones, it can create steam-dominated pockets, acid alteration, and gas release through fumaroles. The shallow hydrothermal system is therefore governed not just by temperature, but by the shifting relation between heat, water, and pressure. The chemistry of these fluids changes as they circulate. Hot water is an efficient solvent, meaning it can dissolve materials from the rock it touches. Silica, calcium, sodium, chloride, sulfur compounds, and many other chemical components may enter the fluid depending on the temperature and the rocks involved. As the water rises and cools, or as pressure changes and gas escapes, some dissolved material precipitates, meaning it leaves solution and forms solid deposits. This is how silica sinter builds around many hot springs and geysers, and how other mineral crusts accumulate around fumaroles and runoff channels. The chemistry also affects acidity. In some parts of Yellowstone, water rich in chloride rises relatively directly from depth and feeds neutral to alkaline hot springs. In other places, steam and volcanic gases interact with shallow groundwater to create acidic fluids, which then break down rock into clay-rich mud and produce mud pots and altered ground. The type of thermal feature seen at the surface depends strongly on these shallow chemical pathways. The rock through which fluids move is changed by the process. Hydrothermal alteration is the term for chemical change caused by hot fluids passing through rock. Glassy volcanic material may be transformed into clay minerals, feldspars may break down, silica may fill cracks and cement loose fragments together. In other places, alteration weakens the rock, making it softer and more prone to erosion or collapse. Over time, this creates a shallow crust that is chemically zoned and mechanically variable. Some channels become sealed by mineral deposition, forcing water to find new routes. Other zones become more permeable as earthquakes or local stress open fractures. The hydrothermal system therefore rebuilds its own plumbing repeatedly. A spring may decline because its conduit becomes clogged with mineral deposits. Another vent may appear nearby where pressure opens a new path. Change at the surface often reflects this quiet reorganization below. Because the hydrothermal system is so extensive, it influences the larger behavior of Yellowstone in important ways. Ground deformation in some parts of the caldera can be explained partly by pressure changes in shallow fluid reservoirs. Earthquake swarms may be encouraged when fluid pressure changes along fractures reduce the force resisting slip. Heat flow from the crust to the surface is also carried largely by moving water, rather than by conduction alone. Conduction is the direct transfer of heat through a material without bulk movement. In Yellowstone, conduction matters, but hydrothermal circulation transports heat much more efficiently in many shallow zones. This is why thermal basins can remain so active over long periods. Water is constantly moving heat from depth toward the surface. Gas rising through the hydrothermal system adds another layer of complexity. Carbon dioxide is especially important. It can be released from deeper magmatic sources and then travel upward through fractures and water-bearing zones. Some of it dissolves into groundwater. Some escapes directly through soil and thermal vents. Sulfur-bearing gases also contribute, especially in areas where steam condenses near the surface and forms acidic fluids. The presence of such gases does not by itself indicate imminent eruption. Yellowstone has long been a degassing volcanic system. Still, changes in gas output can offer useful clues when considered together with seismicity, deformation, and thermal observations. What matters scientifically is not the existence of gas alone, but whether its amount, location, or composition changes significantly over time. The hydrothermal system is also fragile in a practical sense. Shallow ground in active thermal areas can be thin, soft, and unstable because hot water alters the supporting rock beneath the surface crust. What appears to be firm ground may be only a brittle mineral shell over boiling or near boiling water and mud. This fragility shows how closely the hydrothermal world is tied to shallow structure. The same processes that build beautiful terraces and vivid springs can hollow, weaken, or rework the subsurface, even on a small scale. Yellowstone's ground is being continually remade by the circulation of hot fluids. Yet for all its activity, the hydrothermal system remains only part of the volcanic structure. It is a shallow expression of deeper heat rather than the deepest source itself. Its significance lies in how effectively it transfers heat, redistributes pressure, alters rock, and reveals the continuing activity of the crust above the magma-bearing zones. Water enters as snow and rain. It descends through fractured rock. It warms, changes chemically, rises again. and returns to the surface carrying minerals, gases, and heat. In doing so, it forms a moving layer between the visible landscape and the deeper magmatic system, a layer where stone, water, steam, and dissolved matter remain in constant exchange beneath the Yellowstone Plateau. Below Yellowstone's upper crustal reservoir, the volcanic system extends into a deeper zone of hot, partly molten material within the lower crust. This deeper reservoir is not visible at the surface and cannot be sampled directly, yet several lines of evidence indicate that it exists as a broad region of elevated temperature and partial melt beneath the shallower storage zone. Like the upper reservoir, it is not best imagined as one open chamber filled with liquid magma. It is a large and complex body of hot crustal material, containing melt in varying proportions, interacting with surrounding rock and supplying heat upward over very long intervals. At this depth, Yellowstone's magmatic system becomes less affected by the details of shallow hydrothermal circulation and more defined by the long-term transfer of heat and melt through the crust itself. The lower crust is different from the upper crust in both temperature and mechanical behavior. Under greater pressure and heat, rock becomes less brittle and more able to deform slowly without breaking. This style of behavior is often called ductile flow. Ductile means that a material can bend or stretch over time instead of cracking suddenly in Yellowstone's deeper crust. This matters because magma and hot rock are moving through an environment that can accommodate pressure more gradually than the shallow, brittle crust above. Fractures still matter in some places, but the dominant behavior changes with depth. Instead of frequent sharp cracking, there is more slow adjustment, partial melting, crystal growth, and thermal weakening across broad zones. The deeper reservoir belongs to this hotter, more plastic layer of the crust. Geophysical imaging suggests that this lower crustal region beneath Yellowstone is larger than the upper crustal melt-bearing zone above it. Seismic waves passing through it slow noticeably, indicating hot material and partial melt over a wide volume. The amount of melt is thought to vary from place to place, and much of the zone is still likely crystal-rich rather than fully liquid. Even so, the lower crust appears to contain enough partial melt to act as an important long-term source of heat and fresh magma input. This deeper body does not erupt directly to the surface in its full form. Instead, it feeds the upper system over time, contributing material that may rise, stall, mix, crystallize, and evolve before reaching shallower levels. The upper and lower reservoirs are therefore connected, but they are not identical in state or function. One useful way to understand this relationship is to think in terms of supply and storage. The lower crustal reservoir acts more as a long-duration supply region, where heat and melt are maintained on a broad scale. The upper crustal zone acts more as an intermediate storage and evolution region, where magma becomes cooler, more silica-rich, and more strongly affected by crystallization and gas behavior. Fresh input from below can enter the upper reservoir in pulses or repeated smaller additions. These additions may not create immediate visible change at the surface, yet over time they help keep the upper crust thermally active. Without deeper replenishment, shallow, partially molten zones would cool and crystallize more completely. Yellowstone's continuing heat flow and long-lived volcanic unrest indicate that the system is still being sustained from below. As magma rises from deeper levels into the lower crust, it may undergo a process called underplating or intrusion. Underplating refers to magma accumulating near the base of the crust, while intrusion refers more generally to molten rock entering and cooling within pre-existing rock. In Yellowstone, repeated intrusion over long timescales likely contributes to a thickened and thermally modified lower crust. Each pulse of basaltic or less evolved magma from below brings new heat. Some of that material may remain in the lower crust and crystallize there. Some may partially melt surrounding crustal rock. Some may contribute melt upward into the shallower rhyolitic system. This repeated addition helps explain how Yellowstone can maintain an upper crustal reservoir rich in evolved magma. The lower crust acts not only as a source of heat but also as a processing zone where mantle-derived magma interacts with crustal material. That interaction is important because Yellowstone's erupted rhyolites are not simply unmodified basalt rising straight from the mantle. The chemistry of the system indicates extensive crustal evolution. As hotter basaltic magma enters the lower crust, it cools, crystallizes, and transfers heat to the surrounding rocks. That heating may cause parts of the crust itself to melt. The resulting melts can mix with or evolve separately from the original mantle-derived material. Over time, this produces more silica-rich magma suited to the Yellowstone style of volcanism. The deeper reservoir is therefore a zone of transformation as much as of storage. It helps convert incoming mantle heat into the crustal magmatic character seen in the Yellowstone Plateau. Pressure and buoyancy influence how material moves upward from this deeper level. Buoyancy is the tendency of hotter or less dense material to rise relative to denser surroundings. Melt-rich regions in the lower crust may become buoyant enough to send magma upward through dikes, which are sheet-like intrusions that cut across older rock. Yet not every parcel of melt rises freely. Some cools and crystallizes before traveling far. Some may stall where density contrasts. Structural barriers or stress conditions prevent further ascent. This uneven transfer is one reason Yellowstone's system remains distributed across multiple levels rather than collapsing into one simple vertical conduit. Material is supplied upward, but it is stored, modified, and delayed along the way. The lower crustal reservoir also helps explain the longevity of Yellowstone as a volcanic center. Surface eruptions have been intermittent, and major caldera-forming events are separated by long intervals. Yet the system remains thermally active for hundreds of thousands to millions of years. Such persistence requires a heat source capable of operating over very long durations. The deeper crust provides a buffer and reservoir for that heat. It releases energy upward gradually, maintaining partial melt and elevated temperature in the overlying crust even when no eruption occurs. In this sense, Yellowstone's volcanic life depends as much on deep sustained input as on any single eruptive event. Although scientists have strong evidence for the deeper reservoir, uncertainty remains about its exact geometry, melt fraction, and rate of replenishment at any given time. Seismic and electrical studies provide images of anomalous zones, but those images must be interpreted carefully. They indicate hot and partially molten material, yet they do not show every internal pathway in direct detail. Observations support the existence of a deep magmatic body that feeds the shallower system. It remains uncertain how that feed varies in time and how efficiently melt is transferred upward during quieter and more active periods. This uncertainty does not weaken the broader picture. It defines the limits of what can presently be resolved. At this depth, Yellowstone's interior appears less like an isolated shallow volcano and more like a vertically connected magmatic system rooted in the lower crust. The deeper reservoir stores heat on a large scale, receives new input from below, transforms that input through interaction with the crust, and sustains the upper magma-bearing zones over long spans of time. It is a hidden foundation of the Yellowstone volcanic system, broad, hot, and only partly molten, working slowly beneath the plateau to maintain the deeper thermal engine of the region. below the crust, beneath both the shallow and deep magmatic reservoirs. Yellowstone draws heat from the mantle. The mantle is the thick layer of rock that lies beneath Earth's crust and extends downward for thousands of kilometers. Although it is solid on short timescales, it can flow very slowly over geological time under high temperature and pressure. The mantle is not molten in a general way beneath Yellowstone. Instead, the important point is that parts of it are hotter than the surrounding mantle and capable of supplying heat, and some melt upward into the base of the crust. This deep thermal source is central to Yellowstone's existence as a long-lived volcanic system, yet it is also one of the areas where scientific language must remain especially careful. Observations strongly support an anomalous mantle heat source beneath the region. It remains uncertain exactly how narrow, continuous, or plume-like that source is in its full depth and shape. The word plume is used in geology for an upwelling of unusually hot mantle material that rises from greater depth because it is less dense than the surrounding mantle. In the simplest picture, a mantle plume is imagined as a vertical column of a hot rock rising steadily from deep within Earth, perhaps from near the boundary between the mantle and the core. In public description, this image is often drawn as a narrow torch-like feature feeding a volcano directly above. Yellowstone is more complex than that simplified image. Evidence from geophysics, volcanic history, and regional tectonics indicates that Yellowstone is associated with a deep mantle thermal anomaly. But the exact form of that anomaly has been studied and debated for many years. Some observations are consistent with a plume-like upwelling that extends deep into the mantle. Other observations suggest a broader, tilted, or more irregular structure influenced by surrounding mantle flow and the motion of the North American tectonic plate. One of the strongest pieces of evidence for a deep mantle source is the Yellowstone hotspot track. As the North American plate moves southwestward over millions of years, a sequence of major volcanic centers appears progressively across what is now the Snake River Plain, ending at present-day Yellowstone in the northeast. This age progression is difficult to explain without a persistent source of heat relative to the moving plate. Older calderas and volcanic centers lie to the southwest, while the youngest and currently active volcanic center lies beneath Yellowstone. The broad pattern resembles other hotspot tracks on Earth, though Yellowstone differs from oceanic hotspots because it rises beneath thick continental crust rather than oceanic crust. That continental setting strongly affects the kinds of magma produced and how the crust responds to the heat. Seismic imaging has provided additional support for a mantle source. Earthquake waves passing through the mantle beneath Yellowstone show zones of reduced seismic velocity, meaning the waves travel more slowly than they do through colder surrounding material. Such slowing usually indicates elevated temperature, partial melt, or compositional differences. In Yellowstone, seismic tomography, which is a method of imaging the interior by using many seismic wave paths, has revealed an anomalous mantle zone extending downward beneath the volcanic region. Some studies suggest that this anomaly continues to substantial depth, supporting the idea of a deep-seated plume-like structure. At the same time, the images are not simple. The anomaly may tilt, broaden, or vary in strength with depth. The mantle beneath western North America is affected by regional convection, past subduction, and plate-scale deformation, all of which can complicate the shape of the upwelling. Electrical conductivity studies add another line of evidence. Hotter mantle and partially molten regions can conduct electricity differently from colder solid rock. Magnetotelluric measurements, which use natural variations in Earth's electromagnetic field, suggest that the mantle and lower crust beneath Yellowstone contain zones of enhanced conductivity, consistent with elevated temperature and melt or volatile-rich material. These results support the idea that heat and magma are being supplied upward from the mantle into the crust. As with seismic imaging, however, such studies reveal properties, not a simple photograph. They show that the mantle beneath Yellowstone is anomalous and active compared with surrounding regions, while the precise geometry and continuity of the source remain matters of interpretation. The mantle source beneath Yellowstone does not act in isolation. The tectonic setting of the western United States influences how mantle material rises and how crust responds. The surrounding region has undergone long-term extension, meaning the crust has been stretched and thinned in many places. That stretching can help magma ascend by reducing pressure in parts of the upper mantle and crust, and by creating structural pathways for melt movement. Yellowstone also lies within a mantle environment shaped by the earlier subduction of oceanic plates beneath North America. Although active subduction is no longer occurring directly beneath Yellowstone, the inherited structure of the mantle may still influence flow patterns and temperature distribution. This means the Yellowstone heat source is best understood not as a perfectly isolated plume in an otherwise simple mantle, but as an upwelling interacting with a complicated continental interior. Heat from the mantle does not rise to the surface unchanged. As mantle-derived magma enters the lower crust, it cools, crystallizes, and transfers heat into crustal rocks. Some of the magma may remain basaltic, which means relatively low in silica and more fluid. Much of Yellowstone's erupted magma, however, is rheolitic and highly evolved. This indicates that the crust plays a major role in modifying the material supplied from below. The mantle provides energy and magma input, while the crust processes that input into the forms expressed at Yellowstone. In this way, the mantle source is essential but not sufficient by itself to explain the volcanic character of the system. Yellowstone is the product of deep heat, interacting with continental crust over long spans of time. One reason scientific concern focuses on Yellowstone is that the mantle source remains active enough to sustain long-term crustal heat and partial melt. Yet this concern is measured rather than dramatic. A deep heat source does not imply that eruption is imminent. Mantle upwelling operates over immense timescales, and the transfer of heat from mantle to crust to surface is filtered through many stages of storage, crystallization, and fluid circulation. The presence of an active mantle anomaly explains why Yellowstone remains volcanically alive in a geological sense. It does not by itself define what will happen in the near future. Observations indicate ongoing heat supply. It remains uncertain how that supply varies over shorter intervals compared with the very long lifespan of the hotspot. At this innermost depth so far, Yellowstone's volcanic system is rooted in mantle heat that rises beneath a moving continent. Whether described as a plume-like upwelling, or a deep mantle thermal anomaly, the essential scientific picture remains consistent. An unusually hot mantle source lies beneath the region. That source feeds the lower crust with heat and magma, supports the deeper and shallower reservoirs above, and sustains the volcanic and hydrothermal activity expressed at the surface. The exact shape of the upwelling remains an area of active research, but its role as the deep thermal foundation of Yellowstone is well supported. Beneath the forests, lakes, faults, and magma-bearing crust, the system is anchored in a slow mantle ascent that has maintained this volcanic province through vast intervals of geological time. In recent years, scientific concern about Yellowstone has not come from one sudden discovery that overturns all earlier understanding. It has come from sharper imaging, more continuous monitoring, and a clearer picture of how much heat remains stored beneath the plateau. Concern in this context does not mean alarm. It means sustained attention to a volcanic system whose internal structure is now known in greater detail than before, yet still contains important uncertainties. As instruments improve, the Yellowstone system appears neither simpler nor more immediately dangerous than once believed. It appears more complex, more connected across depth, and more capable of subtle change than older simplified models suggest. That increased clarity is itself a reason for concern, because it shows that Yellowstone cannot be understood by watching only surface eruptions or by imagining one large chamber beneath a static crust. It must be watched as an active system in which deformation, earthquakes, gases, fluids, and partial melt all interact. One important area of recent progress has been subsurface imaging, seismic tomography, electrical conductivity studies, and improved gravity measurements have allowed scientists to outline the upper and lower magmatic reservoirs with greater confidence than in earlier decades. These methods do not produce a perfect picture, but together they show a vertically connected system of shallow partial melt above deeper hot crust and mantle-fed input. That picture matters because it confirms that Yellowstone remains a living volcanic field in geological terms. The heat is not residual in the simple sense of a system cooling toward extinction. It is being sustained from below and redistributed through the crust. This does not imply that a large eruption is building now. It does imply that the system has the capacity to remain active for a very long time, and that short-term surface quiet cannot be mistaken for interior stillness. Recent concern has also been shaped by the accumulation of long monitoring records. Decades of seismic, geodetic, thermal, and geochemical observations now allow scientists to compare current behavior with earlier patterns in a much more disciplined way. Ground uplift and subsidence have been documented repeatedly. Earthquake swarms have been tracked in detail. Gas emissions and heat flow have been measured across time. These records show that Yellowstone is restless in an ongoing but usually moderate way. Restless here means persistently active without necessarily progressing toward eruption. The value of the long record is that it defines background unrest. Without that record, a swarm of small earthquakes or a few centimeters of uplift might seem extraordinary. With it, many such episodes can be recognized as part of Yellowstone's established range of behavior. Scientific concern becomes more precise when the difference between ordinary unrest and unusual change is better known. At the same time, some discoveries sharpen concern by revealing how much remains unresolved. The exact proportion of eruptible melt in the upper reservoir remains uncertain. The speed and style of magma recharge from the deeper crust remain uncertain. The relationship between deep gas release, hydrothermal circulation, and shallow deformation remains only partly constrained. Even the shape of the mantle anomaly at great depth is still an area of active interpretation. These uncertainties do not mean that Yellowstone is poorly understood in a general sense. They mean that the system is sufficiently large and complex that no single dataset can describe all its internal changes. Concern arises from this combination of knowledge and limit. Scientists know enough to recognize that Yellowstone is an active magmatic system. They also know that some key transitions, especially those involving melt connectivity and pressure transfer, are difficult to observe directly before they happen. Public discussion often translates scientific concern into dramatic expectation, but professional monitoring resists that pattern. Yellowstone is watched closely not because scientists believe catastrophe is imminent, but because a low-probability, high-consequence volcanic system deserves continuous attention. The most likely future activity, based on the geological record, would not be a giant caldera-forming eruption, smaller hydrothermal explosions, earthquakes, localized deformation, or at some point a more limited lava eruption are more plausible on human timescales, though even these are not expected in any immediate sense without stronger evidence. Scientific concern therefore stays grounded in probabilities and scenarios rather than in spectacle. The system is important because it is active, not because it is assumed to be on the edge of extreme eruption at all times. Hydrothermal explosions are one reason for this measured concern. These events are not driven directly by rising magma in the same way as volcanic eruptions, yet they can occur when pressurized hot water flashes to steam violently in the shallow subsurface. Yellowstone's long history includes evidence of such explosions, some of which leave craters and scattered debris fields. They're usually much smaller than true volcanic eruptions, but they can happen with less warning because they involve shallow fluid pressure and changing permeability rather than magma necessarily reaching the surface. Recent mapping and dating of past explosion craters have strengthened awareness that Yellowstone's hazards include more than magma alone. The hydrothermal system is dynamic enough to create its own forms of localized violence. Concern is also shaped by communication itself. Modern Yellowstone science operates in public view. Data are shared quickly. Monthly summaries describe seismicity, deformation, and notable thermal changes. This openness has clear benefits, but it also means that small variations can be amplified in public imagination. A swarm that lies within normal bounds may be treated elsewhere as evidence of imminent eruption. A new scientific paper refining the size of the deep system may be described as a shocking discovery rather than as part of steady progress. Scientists therefore face a dual task. They must continue to investigate Yellowstone rigorously, and they must explain that rigorous concern is not the same as alarm. Careful monitoring exists because the system matters, not because each new result signals emergency. The phrase seriously concerned is most accurate when applied to scientific responsibility rather than panic. Scientists are serious because Yellowstone is one of Earth's best-known large volcanic systems and one of its most carefully monitored. They are serious because the underground structure contains partial melt, abundant heat, active fluids, and a record of major past eruptions. They are serious because changes in such a system must be detected early and interpreted with discipline. Yet their concern remains bounded by evidence. Observations indicate ongoing unrest and continued magmatic vitality. They do not indicate that a major eruption is underway at present. It remains uncertain exactly how Yellowstone would transition from background unrest to clear pre-eruptive behavior, but the purpose of modern monitoring is to recognize that transition if stronger signs begin to appear. At this stage of understanding, Yellowstone stands as a case where discovery deepens caution without justifying fear. Improved imaging reveals a large connected heat system. Long records reveal persistent but mostly moderate unrest. Hazard studies reveal multiple pathways of surface activity, from hydrothermal explosions to possible future eruptions. Uncertainty remains in the details, especially in how deep processes translate into surface signals. Scientific concern therefore endures not as a sign of helplessness, but as a disciplined response to a volcanic system whose size, persistence, and complexity require constant attention. Yellowstone is taken seriously because the evidence shows a living interior beneath an outwardly calm plateau, and because understanding that interior remains an unfinished task. At the innermost level, Yellowstone is not best understood as separate layers acting alone. Its deep heat, lower crustal melt, upper crustal reservoir, hydrothermal circulation, brittle faults, and moving surface belong to one connected system. Each part has its own behavior, yet no part is fully isolated from the others. Heat rises from the mantle into the lower crust. Melt is generated, stored, and modified there. Some of that heat and material move upward into the upper crust, where magma becomes more evolved, more crystal-rich in places, and more sensitive to the balance between melt, gas, and solid framework. Above that, hot fluids circulate through fractured rock, carrying heat toward the surface and altering the shallow crust through chemistry and pressure. The ground above responds by rising, falling, cracking, and shifting in ways that instruments can measure. Yellowstone's inner reality is therefore not a single chamber or pipe, but a distributed volcanic system whose components remain linked across depth. The deepest source of energy is the mantle anomaly beneath the region. That source supplies heat over very long timescales and helps generate magma that enters the lower crust. Yet mantle heat does not pass unchanged into the upper system. It is filtered through crustal processes. Basaltic magma intrudes into deep crustal rock, transfers heat, crystallizes partly, and can trigger melting in the surrounding crust. The lower crust becomes both a storage zone and a transformation zone. It collects heat, retains partial melt, and prepares the conditions under which more silica-rich magma can develop. Without that deep supply, Yellowstone would cool toward dormancy. With it, the volcanic field remains active in a geological sense even during long intervals without eruption. From the lower crust upward, the system becomes more varied and less uniform. The upper crustal reservoir contains significant partial melt, but much of that melt exists within crystal-rich mush rather than as one large free liquid body. This distinction shapes nearly everything that follows. If the melt fraction is low or poorly connected, the system stores heat without moving easily. If fresh input from below increases heat, remelts some crystalline material, or raises the connected fraction of melt in a local zone, mobility may increase. Gas content matters as well. Dissolved volatiles remain within the melt under pressure, then begin to separate into bubbles as pressure changes. In a viscous silicic system, those bubbles do not always escape efficiently. They can increase internal pressure, change buoyancy, and alter the mechanical behavior of the magma. The reservoir, therefore, evolves through a delicate balance of heating, cooling, crystallization, recharge, gas separation, and melt connectivity. Around and above that reservoir, the crust is not passive. It is faulted, fractured, heated, and chemically altered. Regional tectonic stretching keeps stress active through the surrounding rock. Old caldera structures, ring faults, lava flows, welded ash deposits, and altered zones all influence how pressure is transmitted and where movement is concentrated. Some fractures may act as barriers, others become pathways. A change in pressure within the magmatic system may lead to subtle deformation above, but the exact pattern depends on the strength and structure of the crust. One area may rise, another may remain stable. A fault may slip in a swarm of small earthquakes. A hydrothermal basin may change its discharge. The crust does not merely cover the magma, it shapes how deep changes are expressed. Hydrothermal circulation provides one of the strongest links between the magmatic interior and the surface world. Water enters from snow and rain, descends through permeable rock, warms as it approaches hotter zones, dissolves minerals, and rises again, carrying heat back upward. This process transfers thermal energy much more effectively than conduction alone in the shallow crust. It also redistributes pressure. Mineral deposition seals some pathways while earthquakes and stress changes open others. Steam separates from liquid in some zones. Acidic fluids alter rock in others. The hydrothermal system therefore behaves like a moving interface between magma-heated crust and the surface landscape. It does not create Yellowstone's deep heat, but it reveals that heat continuously and reshapes the shallow crust in response. Because all these components are linked, Yellowstone's monitored signals must be interpreted as parts of one conversation within the Earth. Earthquakes show where brittle rock breaks under changing stress and pressure. Deformation shows where the crust bends or settles as pressure redistributes below. Gas emissions show that heat and volatiles continue to move upward. Thermal features show where hydrothermal circulation remains active. None of these observations alone can define the full state of the system. Together they provide a changing but incomplete portrait of the interior. A swarm may reflect fluid pressure, tectonic adjustment, or magmatic influence, depending on its setting and associated signals. Uplift may reflect hydrothermal pressurization, deeper intrusion, or a combination. Yellowstone requires integrated interpretation because its internal processes overlap rather than separate neatly. This connected structure also explains why Yellowstone can remain restless, without moving directly toward eruption. A great deal of energy is stored in the system, yet that energy is distributed across multiple levels and materials. Heat can drive hydrothermal circulation for long intervals. Pressure can build and release in shallow zones. Faults can slip in swarms. The ground can rise and fall. Meanwhile, much of the magmatic body may remain too crystal-rich to erupt. Restlessness, in other words, is an expected property of a large hot system with partial melt and extensive fluid circulation. It is not the same thing as imminent eruption. At the same time, the system's connected nature means that a meaningful change at depth could eventually influence several monitored signals together. This is why the whole structure is watched carefully. Yellowstone is neither asleep nor in constant crisis. It is active in a persistent, layered way. If eruption were ever to occur again, it would emerge from this interconnected framework rather than from one isolated trigger. Melt would need to become sufficiently mobile and connected in part of the reservoir. Pressure pathways would need to develop through the crust. Gas behavior would matter. Stress conditions would matter. The overlying rock would need to yield. Observations indicate that Yellowstone possesses the ingredients of a major volcanic system. While it remains uncertain how and when those ingredients might align in a future eruptive sequence, that uncertainty is central, not incidental. It is the reason for continued scientific seriousness. The system is understood broadly, yet some of its most important thresholds remain difficult to observe directly before they are crossed. At the innermost level, Yellowstone is a deep thermal engine rooted in the mantle, transformed in the lower crust, stored and evolved in the upper crust, expressed through hydrothermal circulation, and measured through a slowly moving surface. Its parts are different in material and behavior, but they function together. The forests, lakes, faults, geysers, uplift, earthquakes, and melt-bearing crust all belong to one volcanic field whose outward calm rests above a persistent exchange of heat, rock, fluid, and pressure. In that connected interior lies the full meaning of Yellowstone's continuing scientific importance, not a simple hidden chamber waiting in silence, but a complex system in steady motion beneath the plateau. Night settles gently over the Yellowstone Plateau. The forests darken by slow degrees. The broad meadows lose their colour and become soft fields of shadow. Above the lake, the air cools and stills. Steam continues to rise from springs and vents, pale against the dim ground, carrying with it the quiet sign of heat that has been present long before any human record, and will remain long after any single season has passed. The surface appears calm again, as it so often does. Yet the calm is not emptiness. It is the visible stillness of a landscape sustained by processes moving far below ordinary sight. Beneath the cooling air, water continues its patient circulation through cracks and porous stone. Deeper still, the crust holds its stored heat, its crystal-rich melt, its gradual pressure changes, its slow adjustments along faults and old volcanic structures. Far below that, the mantle continues its long upward transfer of energy into the base of the crust. None of this moves quickly in human terms. None of it needs spectacle to be real. Yellowstone remains what it is through persistence rather than haste, through deep time rather than sudden display. The plateau rests under stars, snow, cloud, sun, and long intervals of weather. Rivers continue their courses, sediment settles, forests burn and return, winter gathers and releases, the ground rises a little, then falls, springs change their channels, stone is altered by water and heat. The entire system remains connected, though most of that connection stays hidden from the eye. What is seen at the surface is only the gentlest expression of a much larger interior life. In that quiet balance of land, water, rock, and heat, Yellowstone endures as both landscape and process, outwardly calm, inwardly active, held within the long, steady rhythm of the earth.